actually, wait, we'll get to question 3 first. Okay. Mock time, right. Can you guys see the screen? Let me just arrange my windows. Okay. 2023 mock. A lot of these questions are repeated, so I'm just going to go over the new questions. This question was, I think, in our mock. This was also repeated, so I'll just skip straight to question 2. Supervised learning. The following pseudocode represents one iteration through the training set for gradient descent, univariate, second-order polynomial regression. Assume that the value of the learning rate A is 1. Give the numerical values of all the weights and the cost at the end of the pseudocode for the following training set. Show all your working. Let's just talk about what we got as our values. So what values of cost W0, W1, and W2 did we get for our final values? And if we have any conflicts, we can discuss that. Okay. 5 minus 1 minus 3 minus 7. Yeah, that's what I got as well. So yeah, after one pass, subbing it all in, these are the weights and the cost, and then after the second training data, we get this. Okay, cool. I don't think we really need to go over that. You just trace through this code, and I mean, you can do it with the trace table. You can write it out like how I've written it out, up to you. Just as long as you get the right answer. Okay, 2b, consider a multivariate dataset with 2 classes that are not linearly separable. Is it true that the classes will still not be linearly separable if we remove 1 point from this data? And what about if we remove 1 feature from this data? So let's start with A. If we remove a point from the dataset, would it still remain not linearly separable? No, okay, yeah, so not necessarily. False. Yeah. Okay, what was our justification? What was our justification? 888. 9. If we remove the first 9, then linear set. First line and linear set. Oh, right, yeah, okay. Yeah, so if it wasn't linearly separable, we can think of an example where if we do then remove a point and it becomes linearly separable, we have our proof by contradiction. So Ash has given a sort of 1D example. Here's a 2D example. So if we had this graph here, which isn't linearly separable, and then we remove this x point, all of a sudden now we can linearly separate it with this line here. So it won't necessarily stay non-linearly separable. Only in some cases, yeah. So what I put is it may now become linearly separable. So yeah, we can't guarantee. It's possible that it would still be linearly inseparable, but yeah. Okay. And then for the second part, if we remove a feature from this data, what will happen? No change. Yeah, if we remove a feature, it will just stay non-linearly separable. Just because even though we've removed that, I think one of the answers in the mark scheme was we can imagine it as multiplying that dimension by 0 in our separability formula. And so it's as if it's not there. And so if we can't linearly separate the data in n+1 dimensions, then we definitely won't be able to do it in 1 less dimension. So yeah, if it was linearly separable, then the initial should have been linearly separable. Yeah, if you remove a feature, it compresses the points to a lower dimensional representation, meaning if there wasn't separation before, there definitely won't be now, because there's less dimensions we have to work with for that linearly separable formula. Okay, hoping that makes sense. let's go on to question 3. Okay, so this is an optimization question. Right, let me get my answer. So explain what the constraints are. What are constraints in optimization problems, and how they are usually mathematically depicted in a problem formulation. So what are constraints, and how do we mathematically depict them? Okay, constraints are mathematical conditions that need to be... Okay, let's have a read of this. Constraints are mathematical conditions that need to be satisfied in order for a candidate solution to be accepted in an optimization problem formulation. They consist of the design variables and ensuring that some mathematical equation or function applied to these variables are subject to conditions ensuring feasibility. There can be 0 or more of these constraints. They can only ensure feasibility but also discourage infeasible solutions through constraint handling, like death penalties or levels of infeasibility, in which we can apply a constraint and change our objective function such that it is subject to a constraint that will discourage highly infeasible solutions more than lowly infeasible solutions, which prevent a local optima from being reached and converging. Hence, improving the optimization search formulation, since we look for global optima which are better than local optima in some cases. F of W is the cost function for the linear regression model. This allows us to calculate the cost between the predicted value from the hypothesis function and the output value from the dataset labels. This is known as the mean squared error, MSE, because we square that difference, sum all the differences and average it over all of the distances. And we are trying to minimize the cost in this optimization formulation, which is what we do during gradient descent / training a linear regression model. Okay, I mean, yeah, that's pretty much what I wrote. I'll also paste in what I put. It's not as much of an essay, but I put this. So constraints in an optimization problem define whether or not a candidate solution is feasible or not. We usually mathematically depict them under the objective function, denoted by such that. So for example, max f of x, so this is our objective function, such that, and then constraint equals something, and then constraint equals something. And constraints are typically depicted as some function being equal to, greater than, less than, greater than or equal to, less than or equal to 0. And that's sort of the canonical way we represent constraints in an optimization problem. I don't think they have to, Ollie, but in like all the examples, they always kind of move this to this side so that it's something in relation to 0. Like for example, in the max weight one, it was always sum of the weights minus capital W is more than 0. So I just kind of stick to that now. Strap, okay, yeah. Cool. Go. Love it. Okay. That's 3A. 3B. Consider a regression task represented by a potentially noisy training set as follows, where for any I in 1, 2, up to n, xi and yi are real values. Consider a linear regression model for this regression task. The weights of this model are stored in a 2-dimensional vector, w, of real values, and the output of the model for an input x is given by hxw. Assume that one proposes to formulate the machine learning problem of learning the weights w to be adopted for the regression task as an optimization problem. Explain your understanding of what this f of w function is calculating. So let's paste the question in. What is f of w doing, guys? MSE loss. Cool. Yeah, so we've got this mean squared error loss, and that's because we're calculating the difference, squaring it, and then summing them up, and then this 1 over n just divides it by however many values we had to work out an average. Cool. That's what I put, pretty much. L2 loss, calculates the difference, squares it, adds it up, and divides it to get the mean. Okay, and then II was... Okay, it's down here. Consider that one wishes to solve the problem given by the proposed formulation using simulated annealing with the design below. paste it here. Representation, direct representation of the design variable. In other words, we have a 2D vector of real values. Candidate solution W, where W is just a new vector of size 2. So this is 2 real values. Neighborhood operator. We have some solution. We copy that solution, and then we pick a random weight, so either the first one or the second one, and we either +1 or -1 to that weight, and then we return that. Discuss a key potential weakness of the simulated annealing design in the context of solving the problem given by the proposed formulation. Assume that the proposed formulation truly represents the problem to be solved. Okay, so what is a possible weakness about this design? If I also just go back up to the problem. So we wanted to try and do this regression task. Okay, we've got an answer. Okay, Sid, one potential weakness of the. Let me paste this in. One potential weakness of the design is that a neighborhood operator only allows for local changes in range +or -1. This restricts the algorithm from being able to explore more potential solutions, which may be located in distant regions of the solution space, due to this small range. Without sufficient ability to explore the solution space, the algorithm may converge slowly or potentially get stuck in a local optima, hindering the overall ability to potentially find a global optimum or satisfactory solution. Cool. So, in terms of the + and -1, we said that this was too small of a change to be able to reach a global optimum. I kind of went the other way with this one. So I said, because we're only doing + or -1, the step size might be too big, and we might want to do take more granular steps like 0.1 or 0.01. And so we might skip past potentially good solutions because we're taking those bigger steps. And a visualization for that is if we have something like this, we might step from here down to here, but then we can't actually ever reach here because we can't make those smaller steps. But I guess both these solutions, yeah.
Sorry, I've just got a quick question about this because, like, me and Sid were doing this yesterday.
Yeah.
You know, when we have the value picked uniformly at random from the set 1, 2, is that just the coordinate of I and J? I mean, sorry, W1 and W2.
So this is the weight that we're going to change. So we've got 2 weights, and yeah, so that's just the index of the weight we're changing.
Okay, cool. Thanks.
Just want to check something. So the regression task takes in X and 2 weights. What I was wondering is how come it takes in 2 weights? Like, how come we don't just have 1 weight? Because it's a linear regression and we've only got 1 input. Or I guess, yeah, no. How come the weight is a 2-dimensional vector and not a 1-dimensional one? C. Oh, right. Yeah, no, that makes sense. Yeah, it's weight 0 plus. Okay, yeah, that makes sense. Cool. It randomly chooses which weight to alter and then randomly changes that weight. Yeah, I think what Ash said's right. There's a problem with the actual simulated annealing, not the design itself. 2023 mock Roxy. Yeah.
I had a question about the is the simulated annealing, is there a restriction that you can only change one of the 3 parameters, aka one of the weights, with every neighbor? Or is that just a restriction?
I don't think that's a restriction. That's just in this formulation. Because the
Is
neighborhood
that just
operator
timing it?
Well, it's up to you how you generate your neighbors. It doesn't have to be change one value in this vector. It can be whatever you sort of see as a neighbor can be, as long as you can implement it as a neighborhood operator, then you can do that.
Great algorithm. Okay. Right. Well, in that case, surely we could change multiple weights per neighbor.
Okay.
Which may lead to a better possibility of exploring the solution space. Right now we pick a weight and then change just that weight, whereas we could actually change both the weights by different values.
Yeah, I guess that's how we could improve it. But I think
Yeah,
we
so
just
that
need to
would
talk
be like
about
a
a weakness.
potential. Is
It's just discuss a key potential weakness. But yeah, that would be how
of
we can
simulated annealing or the problem
of
formulation?
this simulated annealing design in the context of this problem. So basically, yeah, this problem formulation.
Okay.
How these two algorithms basically,
Yeah.
and the
So that would
representation.
be so there are no problems with it, but there are just ways it can be improved, right?
Yeah, I feel like that as well.
Like the jump size might be too big. Normally you have like neighbors of like zero point 0.1 or something.
Yeah, but it could also be too small. Like we don't have enough context, I'd say, because all we're told is it's a
Yeah.
linear regression problem. So I'd probably err on the side of one of these two answers because they both kind of get the same point across. It's just that the
Mhm.
values we've hard coded in might not be suitable.
Could you say one of the weaknesses of this would be um, the objective function is differentiable, therefore it's more suited for a gradient descent than a simulated annealing? Or is
I
that
I'd
wouldn't.
like,
probably say you can't just because the whole point of the question is to talk about simulated annealing and its design rather than
yeah,
having
so
another
like,
function.
yeah,
I
'cause they
just
didn't
didn't want
say,
to
I
type
guess I
that.
get it, because they didn't say compare it with the other ones.
Yeah,
Okay, so is it literally just that, like the step sizes might be too big or too small?
I think so. Yeah. If anyone else has any other suggestions, I'll add them.
Or
But
like just you could edit two weights instead of editing one at a time. I guess that
yeah.
was my only other thing. So.
Someone said, "What about constraints?" I mean, there were no constraints in the original optimization problem, so I don't think talking about constraints would really.
And I think it also says at the bottom, like you have to assume that whatever they've given you is like the true representation of the problem. Like
Yeah.
you can't assume that they've missed out constraints and stuff that you should need to put in.
Hmm. Okay. Shall we move on? What about the potentially noisy? Oh yeah. So when it said potentially noisy,
Oh,
that just
that might have something to do with it.
hmm. What does it mean for a data set to be noisy?
Thing is, being noisy would be an advantage of simulated annealing because it's less likely to like be affected by noise and local like optima.
I guess yeah.
That's why I didn't
Noisy is
get why
just
it
how like
said
volatile
weakness.
it is, right? So like
Noise is just data that doesn't fit the pattern that we're trying to see. So like outliers basically.
yeah. Okay. So yeah, outliers. But I don't know how that would relate to this. I might flag this up in the teams as well and see what
I guess you could
Leonardo
talk
has.
about like how do you know when you do the J, like the plus one minus one? When
Yeah.
you're doing that, because it's only plus one and because it's only minus one, if we add on to like what you said about like how they're too big, because they're too big, it might jump between noise rather than actually I don't know.
You know about putting these questions from these papers onto Teams? I don't know, but I did it once and like the lecturers don't seem to respond to the questions from the papers that they haven't put on Canvas. The only
No, they.
responses I got to that was a bunch of Dubai students asking where we got this paper from. And
No, no, no.
I was like, got it from a WhatsApp
Some
chat, bro.
respond. I mean, yeah, but yeah.
But no lecturers replied to that. They replied to like posts before mine and after my message.
Right. Okay. Let's continue with. Okay, so that was II on question 3. Oh, okay. We've done this question. That's pretty much the whole paper. Um, this was in the mock, I believe. Okay.
We're resuming the recording again. Oh well.
No, hold up. Look at the
Yeah.
questions, they're different. They're
Is this
different. The
different?
first question's different.
Um.
Question 4A. Yeah, look.
Oh. Consider the state space
But
of the
he is
problem
the same though.
by any specific. Right. So, in terms of this, in terms of A, I'd probably say we can have an infinite number of states. I mean, like, how would we represent every possible angle from any state? So, wait, let me just paste this here. Yeah. What other constraint? Would it not be finite? I mean, I guess, because if we think about it, the robotic arm can rotate its links by any value. And so this isn't like an integer or a rational number. That can be any integer. I mean, that can be any real number. So even if we say something like, oh, we can do 1.01 degrees, 1.02 degrees, we can always find a state in between that, like 1.005 degrees. And we can always find a state in between here. Okay, that was not proper maths. We can always find a state in between here and in between here. So, like, we can get infinite amounts of states. We can't, like, exhaustively test every possible angle. So, in terms of formulating a search problem, I feel like, we'd have to... BFS isn't complete. I mean, yeah, it's not complete, but it's also just not doable in the first place. Like, we have to hard code in some... How would we do it, though? How would we decide which states to...
You can go to any state. You can even, like, go to, like, the integer state if you wanted.
Yeah, but
Like,
BFS
you could
goes
start off
level
with
by
0
level,
if you wanted. It's just not complete because you wouldn't, like, you're not guaranteed to find a solution. That's one of the, if you look at the performance and the slides of breadth first search and stuff, it says in completeness, it says that BFS is not complete if you are given an infinite search space. So it would be complete if you're given a finite state space, basically.
Right, okay.
Yeah.
How come it isn't complete? In infinite search? Like, so completeness
Because
is
you
where
actually can't find everything. There's like, sorry, Ash,
What's completeness again?
Basically, completeness means that the ability for an algorithm to find a solution, provided a solution exists.
Right.
However, so what that means in this case is if there is a goal node that exists, you are definitely going to find it. However, if there's an infinite amount of nodes between you and the goal space, you're not gonna guarantee to find it, basically. So
right, okay, yeah, because you can't test infinite possibilities. Okay, that makes sense.
Well, it's gonna hang. Yes. It's the halting
Okay, I
problem.
cross over.
I bet we can reduce this to reduce the halting problem to this.
I bet we can reduce orangeness to this. Yeah, no, that makes sense.
What?
Okay. Right. 4A, 4B and 4C, I think there's no 4C. 4B is the exact same as the other one. Cool. How is that worth 10 marks? Yeah, crazy.
Wait, Shay, did we literally just hit like the last paper of all the papers that we're gonna do?
Yeah, I'm probably gonna do some mocks in VC after, but like no more official review sessions.
Mocks in VC?
Yeah. Let me stop the recording.